Hello, welcome to today's webinar on sensing in extreme environments. My name is Daniele Naudi. I'm CTO at SMARTEC, and today we will cover different topics related to fiber optic sensing in extreme environment. In this webinar, my voice should come through your PC speaker or headset. The webinar itself will last about half an hour. And during the presentation, or at the end of it, you can ask questions by typing them in the question panel that you will find on the right-hand side of your screen. And I will answer those questions at the end of the presentation, or if it requires more information, I will do that at the end of the presentation by email. Also, after the webinar, we will send the presentation in PowerPoint, and you will find the video recording of the webinar on our website. So let's get started. Today we will cover different types of extreme environments. I will discuss using sensors in cryogenic temperatures, in high radiation environments, in vacuum, and in the presence of strong magnetic fields and other type of electromagnetic interference. I will also cover several application examples, and as mentioned, we will finish the presentation with a question and answer session. The bulk of the presentation will be based on using fiber optic sensors. So why are these sensors useful for monitoring in such environments? First of all, they are small. The sensors themselves and the cable can be made very small. So they are easy to install in crowded environments. We can measure a number of different parameters, as we will see in the examples, physical quantities like temperatures, displacement, strains, tilts, etc. And they are insensitive to electromagnetic interference, being optically encoded. So that's a big advantage for such applications. Also, some type of sensor can be distributed or multiplexed, so you can have a large density of sensors using only a few cables, and they have been proven to operate reliably in demanding environment such as those as we will discuss today. So let's start with cryogenic application. Cryogenics is the science studying very low temperatures. So typically we start talking about cryogenic at temperatures below minus 150 degrees C. And these temperatures are encountered in different areas, in particular for liquefied natural gas. That's a way to transport and store natural gas in liquid form by cooling it down. Also in physics, we find liquid nitrogen or liquid helium that have respectively 77 or minus 196 Celsius for nitrogen and 4.2 Kelvin or minus 269 Celsius for liquid helium. And these two temperatures are very useful for a number of applications. And finally, the absolute zero, so the lowest possible temperature that can be approached but never touched, is 0 Kelvin or minus 273 degrees C. So where are these fluids or temperature used? First of all, as mentioned, for LNG pipelines. So it's a way of transporting LNG, for example, by ships or by pipelines. And it's also stored in tanks that can be onshore or offshore. Also, the very low temperatures are used for inducing superconductivity in special materials that become superconductor or show zero electrical resistance at this temperature. So these superconducting magnets are used, for example, in physics experiments such as ITER, in particle accelerator such as CERN, or in more industrial applications such as biochemistry for spin resonance testing. Finally, very low temperatures are also used to simulate space-like conditions. So for example, for testing spacecrafts or satellites, there are some rooms where very low temperatures and vacuum can be created to simulate those space conditions. So when using sensors in cryogenic condition, there are some special features that are necessary. First of all, we need to choose the materials that are used to build the sensor appropriately. And in particular, we need to take care about differential thermal expansion coefficients. So different materials shrink at different rates when cooled down. And so this can create stresses or even destroy sensors if that's not done properly. Also, the sensor can be subjected to thermal shocks. For example, if you immerse them in liquid nitrogen, they might not cool down uniformly or slowly. So they need to survive such shocks. For example, our sensor are typically tested 10 times in liquid nitrogen. So we cycle temperature between room temperature and liquid nitrogen 10 times to make sure that the sensor can take that kind of stress. And finally, every sensor can be a temperature sensor if not done properly or if you don't compensate temperature properly. And so we need to make sure that in the presence of such large temperature changes, we don't induce measurement errors. The second type of difficult environment that I'd like to discuss is radiation. Radiation can be of different type, but mostly we're interested in environments that show gamma or neutron radiation. And this type of radiation is typically found either in fission reactors, so traditional nuclear power plants, in fusion reactors, such as ITER or other tokamak fusion reactors. They are found also in nuclear waste storage facilities, in particle accelerators, and for scientific and medical application of radiation, for example, for radiation therapy or other uses of medical uses of radiation. So if we would like to use sensors in radiation environment, and in particular fiber optics, we need to take care of several issues. First of all, we need to make sure that all the materials that are used to build the sensor do not degrade with radiation. For example, some material can become brittle or break or show other type of degradation. And also, you want to make sure that the radiation itself doesn't induce a drift in the measurements. And for that reason, we test our sensors at 5 megagray total dose to make sure that these effects are not introducing any unwanted effect. And finally, fiber optic or normal optical fibers are known to become dark in the presence of radiation, so the losses of the fibers increase, and that can affect the measurement up to the point where the measurement becomes impossible. So for this, we use special fibers that are called radiation hard fibers and are really designed to operate in those environments without suffering significant increases in the losses. Another difficult environment is vacuum. There are different levels of vacuum, as you can see in the table. So we go from atmospheric pressure to low vacuum, medium, high vacuum, and ultra high vacuum. So some between the low and medium vacuum are typically used for isolating things, like for example, making sure that the inside temperature and the outside temperature can be different by creating a vacuum barrier. Ultra-high vacuum is typically found in particle accelerators and such facilities where you have a beam that shouldn't interact with any gas particles. So in that case, the vacuum is very, very it's very, very high. So applications of vacuum that are of interest for sensing include fusion reactors, space testing, particle accelerator, and scientific research in general. So when using sensor in vacuum, one needs to make sure that the materials that are used are compatible with vacuum, so that they don't degrade in vacuum, they don't induce drift to the measurement due to the vacuum, but also we need to make sure that the sensors themselves do not affect the vacuum. So for example, we need to make sure that the sensors are properly cleaned and are not degassing or releasing any gas into the vacuum atmosphere. Also, typically, the measurement units are placed outside the vacuum environment, so we need to provide feed-throughs that can connect the inside of the vacuum vessel where the sensors are placed with the outside world where the measurement unit is placed as well. And finally, vacuum can be lost very quickly, so the pressure changes can be rapid, and the sensor need to survive that type of rapid pressure change. Finally, I'd like to discuss applications of sensor in magnetic fields and other electromagnetic disturbance. There are several problems associated with that, and although very often we claim that fiber optics are insensitive to magnetic fields and electromagnetic interference, there are still some peculiarity that one must take into account. Typically, we would use those sensors into strong magnetic fields, such as those created by superconducting magnets, or also in the presence of rapidly varying magnetic fields, for example, used to induce currents. So these will also induce strong magnetic interference. Typical applications are fusion reactors, particle accelerator, electrical power industries such as transformers or power lines, material testing, and biomedical applications. Since the measurements in fiber optics are done optically, there is no direct effect of magnetic or electromagnetic interference to the measurement. However, for example, if the sensor itself is made of a magnetic material, then a varying magnetic field can introduce a deformation, and that could produce a drift in the measurement. So you need to make sure that the materials that are used are non-magnetic, so they don't suffer themselves the effect of magnetic fields. So our sensors are tested to have magnetic permeability below 1.05. Also, we use non-metallic cables, so fiber optic cables that don't contain any metal, so that there are no induced currents, and this simplifies the electrical isolation of the sensor, even in the presence of rapidly varying magnetic fields. Now that we covered the basics of extreme environments, I would like to introduce some of the sensors that we have developed to address those environments. And many of those sensors can actually operate in a combination of all of these environments. So in low temperature, in vacuum, in the presence of radiation, and in strong magnetic fields. We have developed sensors to measure displacement, short range, long range, and non-contact displacement. We have sensors to measure strain. We have sensors to measure temperature, either point sensor to measure local temperature or distributed sensor to map the temperature in a certain area. And those sensors are based on multiple fiber optic technologies, including Fabry-Perot sensor, fiber Bragg rating sensor, a SOFO sensor based on low coherence interferometry, laser distance meter, and Raman scattering for distributed temperature sensing. So in this slide, you can see some of the displacement sensor. On the top left, you see a long range Fabry-Perot displacement sensor that can measure about 4 centimeter displacement. The similar sensor based on fiber Bragg rating is on the bottom left. On the top right, you have a short range sensor based on Fabry-Perot and the equivalent in fiber Bragg rating, and those sensors measure typically only a few millimeters of displacement. Here you see pictures of non-contact distance meters. We have two technologies, one based on a laser distance meter, so time of flight measurement, where we can use fiber optics to bring the optical signal inside the vacuum and cryogenic environment and then take it out to measure with the conventional laser distance meter. We also have we also have distance meters that are non-contact but based on SOFO technology. These sensors are much more accurate, so they can measure micron level displacement, again without contact between the two sides of the sensor. Moving to strain, here are two examples of Fabry-Perot and fiber Bragg rating weldable sensor. So these are designed to be attached, for example, on the surface of a structural element that is used to build large magnets and measure the deformations. They are able to measure deformation at cryogenic temperature, but they're especially useful to measure deformation during cool down. So temperature compensation is included in both designs. Temperature sensor to measure temperature itself, again based on Fabry-Perot and Bragg rating for point sensing, and on the right hand side a distributed sensing cable that can be used with the Raman system to measure distributed temperature down to nitrogen temperature. So this sensor can be used to map temperature, for example, inside a magnet or another large structure. Besides the sensors themselves, we can provide a number of accessories that are necessary to use this sensor in real-world application. First of all, vacuum feed-throughs to enable connection between the inside and the outside of a vacuum chamber. We have developed a system that has a very dense array of fibers so that a lot of connections can be made in a small space. The feed-through that you can see here has almost 80 fibers in a very small and compact size. Also cables based on radiation hard fibers, both single mode and multi-mode, with the PEEK coating, so polymer, fully non-metallic, and we can also offer fiber bundles, so where 32 fibers, for example, are bundled together into a cable so that they can be more easily installed when high density of sensors are required. Finally, mechanical accessories include mounting elements, covers to protect the sensor, also to shield them from elements that have different temperature, etc. So all these small details are also important to guarantee a good measurement accuracy. Of course, these sensors and accessories have been qualified in a number of tests. You can see here some pictures of cryostats that have been used to subject the sensor to low temperatures, strong magnetic fields. They've also been tested for radiation. So we've gone through a very stringent testing array to make sure that they really perform well in these critical environments. So in general, the sensors that I presented before of all type are qualified for temperatures between 4.2 Kelvin up to 80 degrees C, except for temperature sensors that typically measure only from 20 Kelvin and above. So they can go to lower temperatures, but the accuracy in the temperature measurement is not very good below 20 K. And for distributed temperature sensor based on Raman, the lowest temperature that we can measure accurately to better than 1 degree accuracy is 80 Kelvin. Radiation, SMARTEC sensor were tested at 5 megagray gamma radiation total dose. They've been tested in vacuum down to 10⁻⁸ torr and in magnetic fields as strong as 6 Tesla. Now I'd like to discuss some projects where those sensors are already being used. ITER is the International Thermonuclear Experimental Reactor that I will discuss in more details. European Particle Accelerator, CERN, with the LHC Magnets. The Oak Ridge Spallation Neutron Source in the United States, and a number of projects in LNG tanks and pipelines, as well as European project that was called CryoBragg that was focused on developing Bragg rating sensors for cryogenic environment. There are also some other applications that unfortunately we cannot discuss because they're confidential. So let's explore some of those applications together. I'd like to start with the CERN project because it was the first project where we encountered cryogenic temperatures. It started more than 10 years ago when we were called to provide a possible solution to monitor large superconducting magnets for the LHC collider. Here you can see a picture of the magnets themselves, the so-called dipoles. And these dipoles are installed inside a vacuum tube, and the customer wanted to measure the relative displacement between the magnet and the vacuum tube itself, because it's difficult to observe from the outside. So the requirement was to measure over a distance of approximately 150 to 200 millimeters, and the measurement base was at the cryogenic temperature on one end and at room temperature on the other. So a non-contact measurement was ideal, so that no thermal contact between the two sides was necessary. Additional issues were related to the fact that the cold mass or the magnet contracts during cool down and moves laterally and rotates. And of course, the measurement needed to be carried out in vacuum. So here you can see another picture of the magnet or the cryostat that is now inserted into the vacuum tube, the blue one. And we are installing the sensors. And on this picture, you can see the position where the sensor were installed. The yellow arrows show the measurement base and the sensors themselves that are attached to the vacuum wall, whereas a mirror was installed on the cold mass, and we could measure very accurately the distance between the mirror and the sensor itself. So these sensors were used during the qualification test of the superconducting magnets. And here's an example of result where you can see, for example, the measurement of deformation on the left side and on the right side. So these are the blue and pink curve. So you can see that during temperature decrease, that is indicated by the red curve, the cold mass moves from one side to the other. But at the end of the cool down, you can observe here at the end on the center position that is depicted in green. It comes back to about the same position as initially. So during cool down, it moves a little bit left and right, but then it comes back to the initial position, which is good news. Also, when we subtract the measurements from the two sides, we can measure the contraction of the cold mass due to the cool down, and you can see that the diameter goes down from 0 to -1 millimeter. So there's a contraction of about 1 millimeter on the diameter of the cold mass itself. Another very interesting project that we are currently working into is the ITER project. It's currently under construction in Cadarache in southern France. And this very large experimental fusion reactor uses superconducting magnets, and these magnets will be monitored by a very dense array of sensors. There will be more than 1,000 sensors, and 80% of those sensors will be fiber optics, and these fiber optic sensors are currently supplied by SMARTEC and Fiber Sensing Consortium. So after a very long qualification phase, we are now in the process of delivering the sensor. There are about 700 sensors, including strain, displacement, and temperature. And as mentioned, the sensor had to go through a very stringent qualification program that lasted about 3 years. But right now we are in the phase of delivering the serial production of those sensors. The sensors are used in particular to monitor the magnets themselves, but also the support structures where the sensor that carries the magnets. Here you have a few drawings or pictures of such parts that will be monitored. So for example, on the right hand side, you see two of the toroidal field coils with their optical displacement, optical strain, and optical temperature sensors. Also, there's a schematic of the cable connection that goes first to a local patch panel, then using the fiber bundles that we discussed, will go to the vacuum feed-through that finally connects to the outside world. Other examples of instrumentation include movement of the central solenoid and of the supports of this central magnet. So in this case, we use displacement sensor to measure relative movement of mechanical parts. There are also some sensors that are designed to verify that the bolted connections are not moving. So these sensors are supposed to measure nothing. So in case they will measure any displacement, it would be an indication that one of the bolted connection might have an issue. Other parts that require monitoring are the feeders. Feeders are lines that carry this current to put the current into the magnets themselves. And also these lines contract and expand when the whole system is cooled down to cryogenic temperature. You see on the bottom left side picture, these S-shaped elements are used to compensate for thermal expansion of the bus bar itself. And the deformation of these elements will also be done with the long range displacement sensors. Finally, there are smaller coils called the correction coils that are also monitored in particular with temperature sensors. Another application example of fiber optic sensing technology is for the study of materials that are used in cryogenics. So here you see a fiber optic sensor that are installed on a number of different materials, and they are then cooled down to liquid helium temperature and subsequently subject to strong magnetic fields. First, we can see the effect of cooling down. So on the left-hand side, you see the almost 0 Kelvin temperature, and on the right-hand side, at 300 degrees C is the room temperature. So you see the different materials show different type of compression. The top curve in blue is a fiber optic sensor not mounted on anything. So it has some compression, but not as much as the other materials. And those below include aluminum, steel, composite materials, and some superconducting materials, including tin niobate and titanium niobate. You can see that most of these materials show very little deformation below 50 Kelvin. So also at this temperature, it's interesting to measure strain that are induced by movements due to other reasons. In this graph, we see what happens when we apply a magnetic fields of 6 Tesla. So we claim that optical fibers are not affected by magnetic fields, and that's indeed the case for sensors that are not mounted on anything or are mounted on non-magnetic materials. But if the sensor is mounted on a material that is magnetic, then it will respond to the application of the magnetic field. So this is a very nice example of using fiber optic sensor, because we can really see the effect of the magnetic field on the material without having the sensors themselves affected by the magnetic field presence. Finally, I'd like to show let's say more industrial application. We move away from science and more into industry. Here you see pictures of surface storage tanks for liquefied natural gas. In this example, it's a project in Spain. These reservoirs are typically made of two vessels, one inside the other. The outside vessel is made of concrete, and the inside vessel is metallic. And there is some isolation between the two. So we can use a number of different type of sensor to monitor the different parts. For example, vibrating wire and strain gauges and piezometers are typically installed in the concrete element. Also, deformation, multi-point deformation sensor monitor the foundation, and fiber optic sensors are used to monitor the relative displacement between the concrete and the metallic tanks. Here you see in more detail an example of the installation of an FOD, a Fabry-Perot displacement sensor that measures horizontal and vertical displacement of the inner wall that contains the LNG. This sensor lives in the annular space between the two tanks, and this space is filled with perlite or other type of isolation materials, and so they need to be protected also mechanically, so that these isolation material doesn't affect the sensor performance. That's why the sensor itself is very small, but around it there's a lot of other mechanical elements that are used to protect the sensor and the cables and connect it to the outside. So here you see some pictures of installation. So on the left hand side you really see a top-down view of the annular space before it was filled with the isolation material, and then on the bottom picture of the connection box that is installed outside and then connects the sensor to the readout unit that can be placed in office or rack that's somewhere at room temperature. So this brings me to the conclusion of my presentation today. I have presented some sensors that are adapted to measure displacement, strain, and temperature in difficult environments, including cryogenic temperature, high radiation, vacuum, strong magnetic fields, and other electromagnetic interference. These sensors are now standard products, and they have been used in a number of different applications. And in the link here below, you can see, for example, a publication that was done by ITER on the qualification program on our sensors. So with this, I thank you for your attention today. And again, if you have any question, please use the question panel and I'll be happy to answer those questions immediately. Thank you.